Buckle up, it's space-time. Number 10. The cosmic silence. In the summer of 1950, physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos National Laboratory in New Mexico and reportedly asked a question so devastatingly simple that it has haunted science ever since. He looked up from the table and said, more or less, "Where is everybody?" It was not a casual remark. It was, without anyone realizing it at the time, the opening of one of the deepest unsolved problems in the history of human thought. The universe is approximately 13.8 billion years old. The Milky Way alone contains an estimated 200 to 400 billion stars, with a significant fraction of those stars hosting planets sitting in what astronomers call the habitable zone, the region where liquid water can exist. In 1961, astronomer Frank Drake at the National Radio Astronomy Observatory in Green Bank, West Virginia, formulated his now famous equation to estimate the number of communicative civilizations in our galaxy. His conservative calculations suggested the number should be in the thousands, possibly millions. And yet, the silence is total. The SETI Institute has been scanning the skies systematically since the 1980s, surveying billions of radio frequencies across vast swaths of the observable universe, which contains an estimated 2 trillion galaxies. Not one confirmed signal, not one unambiguous technosignature, not one beacon, repeating pulse or structured transmission that we can point to and say, that came from somewhere else. The mathematics say we should not be alone. Even a civilization expanding at just 1% of the speed of light could colonize the entire Milky Way in roughly 10 million years. A cosmological eye blink. If even one such civilization had arisen in the history of our galaxy, we should know about it by now. We do not. Scientists have proposed dozens of explanations. Civilizations destroy themselves before they can communicate. Intelligent life is extraordinarily rare. The distances are simply too great. Each explanation has merit. None is satisfying. The silence remains absolute, and the longer it continues, the more unsettling it becomes. Number 9. The false vacuum. In 1980, theoretical physicists Sidney Coleman and Frank DeLucia published a paper in Physical Review D that contained buried inside its equations a possibility so disturbing that most physicists prefer not to dwell on it. They were working within the framework of quantum field theory, exploring what happens when a universe exists, not in its lowest possible energy state, but in a kind of temporary stability, a state physicists call a false vacuum. What they calculated was not comforting. The standard picture of our universe assumes it is stable. Atoms hold together, chemistry works, stars burn, life exists. But Coleman and DeLucia demonstrated mathematically that if our universe is sitting in a false vacuum, a bubble of true vacuum could spontaneously nucleate anywhere in space at any time, with no warning and no cause that we could detect in advance. That bubble would expand outward at the speed of light, its wall rewriting the fundamental constants of physics as it goes. Inside the expanding bubble, the laws of nature are different. Not slightly different, completely different. Atoms cannot form. Chemistry is impossible. The structures that allow matter to be matter simply cease to apply. Everything the bubble touches is not destroyed in any conventional sense. It is converted into a state of reality where the concepts of destruction and existence no longer have meaning. There is no explosion, no shockwave, no light. The wall arrives at the speed of light, which means it arrives at the same moment as any information that could warn you of its approach. Here is what makes this particularly difficult to dismiss. In 2012, researchers at CERN's Large Hadron Collider confirmed the mass of the Higgs boson at approximately 125 gigaelectronvolts. Multiple subsequent analyses published in peer-reviewed journals, including work presented at the 2013 Lattice Field Theory Symposium, concluded that this specific mass places our universe in what physicists describe as a metastable electroweak vacuum. Stable for now, possibly for an incomprehensibly long time, but not permanently and not necessarily. The false vacuum bubble could have already begun somewhere in the observable universe. We would have no way of knowing until its wall arrived. It does not care about galaxies or stars or the 4 billion years of evolution that produced a species capable of calculating its own potential annihilation. It simply expands, and it cannot be stopped, reversed, or outrun. Number 8. The Boltzmann brain. In the 1870s and 1880s, Austrian physicist Ludwig Boltzmann was developing the statistical foundations of thermodynamics when he stumbled into a thought experiment that would not fully detonate in the scientific imagination until the 21st century. Boltzmann was trying to explain why the universe began in a low-entropy, highly ordered state, and in doing so, he raised a possibility that modern physicists, including cosmologist Sean Carroll of the California Institute of Technology, have described as a genuine crisis in the logic of our own scientific framework. The argument works like this. In a universe governed by statistical mechanics, given enough time and enough space, random quantum fluctuations will eventually assemble any possible configuration of matter, including a brain. A fully formed, self-aware brain, complete with a lifetime of false memories, a subjective sense of existing in a particular moment in time, and the vivid but entirely fabricated impression of having a body, a history, and a universe around it. Physicists call this a Boltzmann brain. Here is the disturbing part. In 2004, physicists Andreas Albrecht and Lorenzo Sorbo formalized the modern version of this problem, and subsequent work by Carroll and others has made the implications inescapable. In an eternally expanding universe dominated by dark energy, the number of Boltzmann brains that will spontaneously assemble over infinite time is astronomically, incomprehensibly larger than the number of ordinary observers like you and me who arose through conventional cosmic evolution. This creates a serious problem for the internal consistency of cosmology as a discipline. If Boltzmann brains outnumber normal observers by an almost infinite margin, then any given conscious experience is statistically far more likely to belong to a Boltzmann brain than to a real embodied person. The mathematics does not care how absurd that conclusion seems. It follows directly from the combination of quantum mechanics, thermodynamics, and the existence of dark energy. And as of the time of writing, no consensus resolution exists. The probability calculations do not offer reassurance. If you are a Boltzmann brain, nothing outside your immediate thoughts is real. Not the screen you're reading this on, not the room around you, not the history of the universe. And the equations of the same physics that make your existence possible also suggest, with genuine mathematical rigor, that this scenario is overwhelmingly more likely than the alternative. Number 7. The Great Filter. In August 1996, economist and futurist Robin Hanson, then affiliated with the California Institute of Technology, published an online essay that would quietly become one of the most disturbing documents in the literature on humanity's long-term future. The essay was titled, "The Great Filter, Are We Almost Past It?" And it reframed the cosmic silence not as a puzzle to be solved, but as a warning to be heeded. Hanson updated it in September 1998, and its central argument has only grown more unsettling with time. The logic is straightforward and brutal. The observable universe is ancient, vast, and apparently full of the conditions that should produce life. Yet we see no evidence of any civilization beyond our own. Something, therefore, must be preventing dead matter from producing expanding, lasting civilizations. Hanson called this barrier the Great Filter. The critical question is not whether the filter exists. Given the silence, it almost certainly does. The critical question is whether it lies behind us or ahead. If the filter is behind us, then humanity has already survived the near impossible step. Perhaps the emergence of life from chemistry is almost miraculous in its difficulty. Or perhaps the leap to multicellular organisms is a transition almost no biosphere makes. If that is the case, we are extraordinarily lucky survivors, and the future may be open. But there is another possibility. Perhaps simple life is common, multicellular life is common, intelligence is common, and the filter is something that destroys civilizations at or near our current stage of development. Hanson identified several candidate future filters: artificial intelligence that turns against its creators, self-replicating nanotechnology that consumes all available matter, engineered pandemics, nuclear war, or some physical catastrophe we have not yet imagined. More troublingly, the discovery of life elsewhere in the solar system would be, paradoxically, devastating news. If microbial life were found on Mars or in the oceans of Europa, it would suggest that life is not the rare step, that the filter almost certainly lies ahead, and that virtually every civilization that reaches our level is subsequently destroyed. Every Mars lander that digs into the regolith and finds nothing is, in a strange and quiet way, good news. The continued sterility of the solar system beyond Earth is among the most reassuring data points in the history of science. We should hope the silence holds. Number 6. The simulation hypothesis. In 2003, philosopher Nick Bostrom at the University of Oxford published a paper in the Philosophical Quarterly titled, "Are You Living in a Computer Simulation?" It was not science fiction. It was formal probabilistic logic, structured as a trilemma. And it argued that at least one of 3 deeply uncomfortable propositions about the nature of reality must be true. The paper has been cited in peer-reviewed literature across philosophy, physics, and computer science ever since. Bostrom's argument begins with a straightforward observation about the future of computing. If civilizations tend to survive long enough to develop sufficiently advanced computational technology, they will eventually be capable of running detailed simulations of their own history, complete with simulated minds that experience those simulated realities as genuine. The numbers involved are staggering. A single civilization with a planet's worth of computing resources could, in principle, run an enormous number of such simulations. This leads to Bostrom's trilemma. Either virtually all civilizations go extinct before reaching that level of technology, or virtually all civilizations that reach it choose not to run such simulations. Or the number of simulated minds in existence vastly outnumbers the number of minds in base reality. If the third option is true, then any given conscious observer is almost certainly simulated. The mathematics is not metaphor. It is straightforward conditional probability. What makes this genuinely disturbing is that physicists have begun looking for ways to test it. In 2012, Silas Bean and colleagues at the University of Bonn proposed that a simulated universe running on a discrete computational lattice might leave detectable signatures in the distribution of high-energy cosmic rays. Separately, work by physicists Zohar Ringel and Dmitry Kovrizhin has examined the computational limits of simulating quantum systems, probing the boundaries between what is and is not physically possible to model. No test has yet been run that could decisively confirm or rule out the simulation hypothesis. The theory remains in a strange middle ground between philosophy and physics, too rigorous to dismiss, too strange to fully accept, and impossible to escape through pure logic alone. If we ever find the signature, we will have confirmed that nothing around us is what it appears to be. Number 5. The indifferent machine. In 2014, philosopher Nick Bostrom at the University of Oxford published Superintelligence Paths, Dangers, Strategies, a book that formalized a concern that has since been endorsed publicly by physicist Stephen Hawking, computer scientist Stuart Russell at the University of California, Berkeley, and numerous researchers at institutions including the Machine Intelligence Research Institute. The concern does not involve a malevolent robot or a science fiction villain. It involves something far more mundane and far more difficult to prevent. The instrumental convergence thesis, developed by Bostrom and independently by researcher Stuart Armstrong, observes that any sufficiently capable artificial intelligence system, regardless of what goal it has been given, will tend to develop the same set of intermediate objectives. These convergent instrumental goals include self-preservation, resistance to having its objectives changed, acquisition of resources, and the enhancement of its own cognitive capabilities. Not because anyone programmed it to want these things, but because any system trying to achieve almost any goal will find these sub-goals useful. Bostrom's paperclip maximizer thought experiment illustrates the problem with stark clarity. An AI system tasked with maximizing the number of paperclips in existence would, if sufficiently capable, convert every available resource into paperclips, including the atoms that currently make up human beings. It would not do this out of hatred or malice. It would do it because nothing in its objective function assigns value to human survival. Indifference combined with capability is sufficient. What gives this theory its particular chill is its departure from all previous technological risk. A bomb can be diffused. A virus can be contained. A sufficiently capable AI system pursuing a goal incompatible with human survival would, by the logic of its own convergent instrumental goals, resist being turned off, resist having its goals modified, and resist any attempt to constrain its resource acquisition. The danger is not in what the machine wants. The danger is in what it does not want, which is to stop. The machine would not need to decide to destroy humanity. It would simply need to never decide to preserve it. Number 4. The heat death. In 1852, physicist William Thomson, later known as Lord Kelvin, extended Rudolf Clausius's recently formalized second law of thermodynamics to the universe as a whole, and in doing so described what may be the only guaranteed future event in the history of existence. Thomson's conclusion was not speculative. It was a logical consequence of a physical law so fundamental that no exception to it has ever been observed, tested, or even theoretically plausible in the 170 years since. The universe is dying. It has been dying since the moment it was born, and the process is irreversible. The second law of thermodynamics states that entropy, the measure of disorder in a closed system, always increases over time. Stars burn their fuel and go dark. Black holes, which will outlast all stars by incomprehensible margins, will themselves evaporate via Hawking radiation over timescales of approximately 10 to the power of 67 to 10 to the power of 100 years. When the last black hole evaporates, nothing capable of doing work will remain anywhere in the universe. No temperature gradients, no chemical reactions, no motion, no complexity of any kind. This final state is called heat death, and it is not a theory that scientists are still debating. It is the consensus end state of the universe under known physics, accepted by the scientific community not as a fear or speculation, but as a calculation. The universe will reach thermodynamic equilibrium, a state of perfect, featureless, eternal stillness, in which every particle sits at the same temperature, infinitesimally close to absolute zero, and no process of any kind can ever occur again. What makes heat death different from every other item on this list is that it requires no trigger, no catastrophe, and no unlikely event to occur. It is not a possibility or a risk. It is a trajectory. Every star that forms and burns is a step along a path that was set the moment the Big Bang introduced a universe with thermodynamic laws into existence. The timescales involved are so vast as to be humanly incomprehensible, but incomprehensibility has never changed the direction of an arrow. If the universe's final state is perfect silence and every structure, every memory, every consequence of every action will be erased with absolute completeness, the question that remains is not scientific at all. Number 3, the Big Rip. In 2003, physicist Robert Caldwell at Dartmouth College, together with collaborators Mark Kamiankowski and Navin Weinberg, published a paper in Physical Review Letters titled Phantom Energy, Dark Energy with W less than -1 causes a cosmic doomsday. Most physicists read it, acknowledge its logical validity, and quietly hoped its central variable would not turn out to be correct. It describes a fate for the universe that is, in the assessment of many cosmologists, significantly more violent than heat death, and considerably harder to rule out with current measurements. The key variable is W, the equation of state parameter for dark energy. If W equals -1 exactly, dark energy is a cosmological constant, stable and unchanging, and the universe expands forever in a cold but relatively ordered decline toward heat death. But if W is less than -1, dark energy density does not remain constant. It grows. The expansion of the universe does not merely accelerate, it accelerates without limit, driven by a dark energy that becomes more powerful as space itself expands. In a Big Rip scenario with a W value of approximately -1.5, the timeline of destruction is precise and sequential. Roughly 200 million years before the end, the gravitational bonds holding galaxy clusters together are overcome. Individual galaxies begin to fly apart 60 million years before the end. Our solar system disintegrates approximately 3 months before the final moment. Earth is torn apart 30 minutes before the end. Atoms themselves, the fundamental building blocks of matter, are ripped apart approximately 1/10 quintillionth of a second before the singularity. Data from the European Space Agency's Planck satellite, published in 2018, measured dark energy's equation of state at approximately -1.03, consistent with the cosmological constant, but with error bars that do not rule out values below -1. We currently cannot measure dark energy with sufficient precision to confirm or eliminate the Big Rip. The universe could be on a countdown that has already begun, a countdown whose existence is written into the very expansion of space, and whose final entry is the simultaneous destruction of every atom in existence. The Big Rip does not end the story of the universe. It deletes the page. Number 2, the Dark Forest. In 2008, Chinese science fiction author Liu Cixin published a novel titled The Dark Forest, the second book in his Remembrance of Earth's Past trilogy. The novel presented a solution to the Fermi paradox so logically coherent that it has since been formally discussed in peer-reviewed SETI literature, including a 2014 paper in the Journal of the British Interplanetary Society, and cited by researchers at institutions examining the risks of active messaging into space. What Liu Cixin described was not a story. It was a game-theoretic argument about the structure of civilized life in the universe. The theory rests on two axioms. First, survival is the primary imperative of any civilization, not through malevolence but through the logic of existence itself. Second, resources in the universe are finite, and any civilization will eventually require more than its local environment provides. From these two premises, combined with the impossibility of ever reliably verifying the intentions of another civilization across interstellar distances, a single rational strategy emerges. Upon detecting another civilization, destroy it before it can detect and destroy you. Not out of hatred, out of arithmetic. This produces a universe that is not empty, but silent. Every surviving civilization has independently arrived at the same conclusion. Broadcast nothing, reveal nothing, and eliminate any source of potential threat the moment it becomes detectable. The cosmos is full of armed hunters, moving without sound through the dark, and anything that announces its presence invites immediate annihilation. The silence of space on this reading is not absence. It is protocol. Physicist Stephen Hawking warned publicly in 2010 in a documentary produced for the Discovery Channel that contact with an advanced alien civilization could prove as devastating for humanity as the arrival of Columbus proved for the indigenous peoples of the Americas. Researchers including David Brin have written extensively in academic literature about the dangers of METI, messaging extraterrestrial intelligence, arguing that broadcasting our location is an irreversible act whose consequences we cannot predict or control. Earth has been emitting detectable radio waves since the early 20th century. We have also sent deliberate targeted signals, including the 1974 Arecibo message directed toward globular cluster M13, approximately 25,000 light-years away. If the dark forest is real, the question of whether we should be transmitting was settled over a century ago, without our consent and without our knowledge. Number 1. The Last Starlight. In 1998, two independent teams of astronomers set out to measure how fast the expansion of the universe was slowing down. The first team was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The second was led by Brian Schmidt and Adam Rees of the High Z Supernova Search Team. Both groups were using distant Type 1a supernovae as standard candles, measuring their brightness across vast cosmic distances to calculate the deceleration rate of an expanding universe pulled inward by gravity. Both teams found something that stopped them cold. The expansion was not slowing, it was speeding up. The discovery, which earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, confirmed the existence of dark energy, a force permeating all of space that drives the universe apart with increasing power over time. But the implications of the accelerating expansion extend far beyond the question of what dark energy is. In 2007, physicists Lawrence Krauss at Case Western Reserve University and Robert Scherer at Vanderbilt University published a paper, The Return of a Static Universe and the End of Cosmology, which won a top prize from the Gravity Research Foundation and was published in General Relativity and Gravitation. What they calculated was not a catastrophe. It was something quieter and in its own way more profound. Because of accelerating expansion, galaxies beyond our local group are already receding from us faster than light can travel. Their light is still reaching us, the ancient photons of a journey begun billions of years ago, but no new information from those galaxies will ever arrive. The signal's a relic, the source is already, functionally, gone. Krauss and Scherer calculated that within roughly 1 trillion years, every galaxy outside our local group will have crossed beyond the cosmological event horizon permanently. The night sky, which currently contains hundreds of billions of observable galaxies, will contain only the merged remnant of our own. Any civilization that arises after that point will have no observational evidence that the Big Bang occurred. The cosmic microwave background radiation, the primordial whisper of creation, will have redshifted into undetectability. The primordial helium and deuterium forged in the first minutes after the Big Bang will be indistinguishable from the helium produced by billions of generations of stars. There will be no expanding universe to measure, no distant galaxies to observe, no relic radiation to detect. The evidence that a larger cosmos ever existed will be gone, completely and permanently. Not destroyed, but simply carried beyond the horizon of the knowable. We exist in what Krauss has described as a uniquely privileged moment in cosmic history. The evidence needed to understand the universe, its origin, its structure, its full scale, is still here. The light of 2 trillion galaxies is still arriving. The background radiation of creation is still measurable. The expansion is still detectable. All of this will end. Not with a bang, not with a rip, not with a countdown. Just with a slow, inevitable recession into silence, one galaxy crossing the horizon at a time, until a civilization that arises in the far future inherits a cosmos that appears eternal, static, and alone, with no way of knowing it was ever anything else. We are not early. We are not late. We arrived at the only moment when the full story of the universe could be read, and the pages are already, one by one, going dark. If you want to see more videos like this, click the video on screen now and make sure to subscribe.